Welcome everyone to this class. This is the official title is Topics in Algebra, but the real title will be Combinatorics of Orthogonal Polynomials. So in this course, we will learn, like I said, combinatorics of orthogonal polynomials. So let me first give you a brief introduction about our class. So this is the course web page. I put the link in the iCampus, but you can also go to, if you go to this web page, then you can go to this link. But alternatively, you can search my name, Jang-soo Kim, in Google, and there should be a way to find the link from there. So important announcements will be posted in this web page. So it'll be nice if you can visit this web page frequently. Okay. So let me go over what there are in this web page. So the overview of this course is the following. So the main topic in this course is orthogonal polynomials. So these are like classical objects, probably dated back to at least Legendre. So it's a very classical object, and maybe because of that, they have been studied a lot by many people in many different areas like classical analysis and mathematical physics, probability, and also in combinatorics. So in this course, we will study combinatorial aspects of orthogonal polynomials. These have been developed in 1980s, and I really think that these are fascinating mathematics there. So I want to share this story with you in this class. So the useful sources of this lecture will be the lecture notes here. So there's a link here. So if I click on it, I will constantly update these lecture notes, so you can download from there. And let's go back. And I also, by the way, I'm recording this lecture, so I'll put these lecture videos on the YouTube. I also put a link here, so you can watch the lectures later. And feel free to leave comments there or questions. I'll be happy to answer your questions there. And also, maybe I can say the main text here in this course will be two of these, like Vienno's lecture notes, but it's written in French, so it might be difficult for you to read. But I will update these lecture notes, so hopefully that will be useful for you. And also, Chihara's book is also about the introduction to orthogonal polynomials, written like 45 years ago. So it's an old book, but it's a very nice book. And I will cover first few sections of Chihara's book, which is more in like analytic point of view of orthogonal polynomials. And then I will move on to the Vienno's lecture notes, which is mostly in combinatorics. So we will be focusing our attention from analytic point of view or just basic orthogonal polynomials, and then we will study how to study them combinatorially using Vienno's lecture notes. So these two are the main sources of this course. And also, there are many lectures delivered by Vienno. So here's also a link. So if you go to the link, you can find many lectures there. So that can also be very useful. And the grading will be determined by class participation and homework. And homework may include student presentation. So at the end of the semester, if we have time, there might be some presentations by you, okay? But I will tell you more later. And the homework will also be announced or posted in this webpage. So yeah, you can check this later. And the schedule and the links to the lecture videos will also appear here. Any questions so far about the class info? Okay, then let's move on. All right. So today we are going to I'm going to give you an introduction. Introduction to orthogonal polynomials. So I will cover the first few sections of Chihara's book. So this is one of them. Oh, by the way, yeah, maybe I should tell you this first. The prerequisite of this course, maybe I forgot this. So you need to, so this is designed for undergraduate students or advanced undergraduate students and master's degree students. So I expect you to know basic things about calculus, linear algebra, and maybe some knowledge in discrete math. But whenever we encounter some new concepts, I will try to review these. So even if you don't remember everything from there, you will have some opportunities to review them. But basically, you need to have some solid understanding of these subjects. Okay. Okay. So first, so what are orthogonal polynomials? That's the main question today. And in fact, if you have learned calculus, you probably already know orthogonal polynomials. Not in the form that you recognize, but you can see this. So in calculus, we know calculus. We know cosine law, addition formula, things like that. So in calculus, we know cosine, let's say, m theta, cosine n theta, 2 equals cosine m plus n theta minus cosine n minus, let me write it here, minus cosine m minus n theta. Okay? You know how to do this. So you can derive this from cosine addition rule. So if you integrate here where mn, let's say mn are non-negative integers. Of course, this is true, but we will assume non-negative integers. Okay. And then let's integrate both sides from 0 to pi. Maybe you can just forget about the 2. And d theta. Then you will realize that this is going to be 0, right? If m different than n. Have you seen this in your calculus class before? This is, just replace this by this divided by 2, and then if you evaluate the integral, then you will get 0 if they are different. So in this case, we say that this is kind of an example of orthogonality. So we say that, so here we say that cosine m theta, cosine n theta are orthogonal. Orthogonal. Over the interval like a 0 pi. Okay? Because that's the way we say usually in the orthogonal polynomial theory. So, but this is not really a polynomial right now because cosine theta is transcendental function, right? It's not a polynomial function. So we want to somehow associate to it a polynomial, but there is a way to do this. We know from again cosine addition rule, cosine n theta is a polynomial in cosine theta, right? It's not a polynomial in theta, but it's a polynomial in cosine theta. For example, like cosine n equals 1, let's say n equals 1, then cosine n theta is of course just cosine theta. What is n equals 2? Cosine 2 theta, so it's like 2 cosine squared theta minus 1. So it's still a polynomial in cosine theta. And if you do this, you can get, the polynomial gets more complicated, but still a polynomial. So, so that means we can write cosine n theta as a polynomial, let's say t sub n, like this, cosine theta. So for example, this means t1 x equals 1 x. This means t2 x equals squared minus 1, like that. So yeah, maybe I should write over here. So t0x equals 1. This is just by definition or by convention. This equals x. T2x equals x squared minus 1. And if you compute further t3x, then you will get things like this. Just elementary computation using the sine law, cosine law. 어디요? Right, yeah, it's a 2. Thank you. 2.
혹시 그거랑 코사인 n 마이너스 에세타 앞에 마이너스가 아니라 플러스가 들어가야 되겠습니다.
You studied calculus well. Well enough. Thank you. Yeah. In my lecture note, I wrote correctly, but yeah. To be honest, I haven't used this formula for a long time, so I don't even remember at all. But yeah, feel free to ask questions. In Korean, in English, okay, I will, yeah, if necessary, I'll translate that question in Korean, in English, yeah. Anyway, no more mistakes. So polynomials appear here, but now instead of this, let's say that okay, let me copy this over here. And then I'm gonna move on. So now let me do this change of variable. Let x equals cosine theta, right? Then we know how to change this. This becomes minus 1 to 1. Because this is now Tm of x, and this becomes Tn of x. And this, if you do this change of variable formula, then you will get something like 1 over square root 1 minus x squared dx. And this turns into this, if m different from n. Okay, so we have two polynomials, the sequence of polynomials, t1, t2, ... And then if you multiply two of them, and two different polynomials, and then if you integrate using this weight function, so to speak, then we get 0. So in this case, we say that this polynomial sequence, so n, let me write it this way. This means n from 0, 1, 2, dot, dot, dot. So sequence of polynomials is orthogonal. Orthogonal with respect to, how can I say? Let me write this way, with respect to weight function. I'm going to define more generally, but let me put it this way. Weight function, this. And these polynomials, Tn, x, these polynomials are called Chebyshev polynomial. So in orthogonal polynomials, there are many well-known functions like Chebyshev polynomials, Hermite polynomials, Charlier or Laguerre polynomials. So we will learn general theory of orthogonal polynomials, and also we will study special orthogonal polynomials like Chebyshev, Hermite. So we will see them more later. Okay, let's see. But by orthogonal, if you have learned linear algebra, you know what orthogonal means. So this is really the same meaning as the orthogonality in linear algebra. So let's recall that. So suppose that V is a vector space or inner product space. So inner product space with inner product. Inner product is given like this. Okay. Then we say that u1, u2, dot, 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 un could be infinite vectors, but let me just use finite vectors. But there could be the list could be infinite. We say that these are orthogonal if this inner product is 0 if you take two different vectors in the list, right? This is what we say a list is orthogonal. So when we say orthogonal, we must have an inner product, things like that. But here, what is the inner product? So in this case, V is the space of polynomial. So this is R. This is field with the bracket. This means the space of polynomials with real coefficient. So if you change this to like C or other fields, that means polynomials with coefficients in that field. And then we define the inner product, fx, gx, to be this integral. We have that measure. Then, so now polynomials are vectors, right, in this vector space, and they are orthogonal if a list of polynomials is orthogonal if they satisfy orthogonality. Like, you take the inner product and they become 0, then it's going to be orthogonal. Okay. So in this sense, this is really the same thing as the same meaning as the orthogonality in linear algebra, right? So the inner product can be defined like this. Okay, now let me define orthogonal polynomials in a general way. So, definition. this is definition that we will use for orthogonal polynomials. Suppose that Wx is a non-negative and integrable say on a comma b. Let's have this condition because we don't want to have vanishing conditions, so this is positive, okay? So if you integrate this function wx, it's going to be positive from a to b. So non-negative means no, it's not negative for every x in this interval. And okay, one more thing. We don't want this to be too big, so this is for all n. Okay. Oh, I forgot this. Okay. Then a sequence of polynomials. So we will write this way. So n, so index from 0. We say that this is an orthogonal polynomial sequence. Orthogonal polynomial sequence, and because it's too long, I will use this abbreviation, OPS. If with respect to the weight function, so weight function, or also called, I will also call this just a measure. If the following condition holds, if the following holds. So first, the degree of the nth polynomial must be n. So basically that means your sequence must be a basis of the polynomial space. Yeah. And second, if you integrate two polynomials like this, and we have measure attached, just like the Chebyshev case, it must be 0 if m different from n. So if two conditions are satisfied, then we say that this sequence is an orthogonal polynomial sequence, OPS. Okay, so this is one way to study orthogonal polynomials, where we have this explicit measure, like Hermite polynomial, Chebyshev polynomial case, we have this measure. But if you think about this more carefully, then you may realize that actually it's not really necessary to have this measure. Because all we need is how to evaluate polynomial, or so. As long as you know how to evaluate polynomial integral of this, then that's all. That's all. So there is another way to study orthogonal polynomials. So let me explain this way. So let me put it this way. There is another way to study OPS. So for a polynomial fx, say, so suppose that we have this situation. So we have orthogonal polynomials, and then we want to kind of extract the essential information we need there. So let's say L of fx is just this integral, a to b f of x wx dx. Okay. Then actually, you don't really have to know this measure as long as you know some information. So let's say then this L of fx is completely determined by the moments. Moments usually denoted by mu sub n, which is just this. Why? Because it's a polynomial, we know that this integral is linear. So if you have, for example, if you want to compute like x squared plus 2x, then what is that? By linearity, it's going to be x squared wx dx plus 2 times x wx dx, right? But this is nothing but mu2 plus 2 mu1. So all you need is this information about the moments. If you know the moments, then that's all. You don't have to know explicit measure. Yeah.
In the second item, does the integration can be 0 given if 8%? Is this sufficient condition?
Oh, you mean here?
Yeah.
Oh, good question. So the question is, don't we need a third condition that this is non-zero? Yeah, that's something that I'll tell you right now. But it is not necessary here in this case because of some conditions that we have here. Because of this. So this means that this weight function has non-trivial non-trivial support. So if you have a polynomial that is strictly positive or non-negative always, then like x squared, then it must be positive. So actually, okay. Yeah, I will explain that in more details in the next page. By the way, this is called the moment sequence. It's a moment sequence. So if you have a sequence of numbers, then you can just define this L so that the moments are this. And then it's linear functional with moments. Then this determines the linear functional defined on on the space of polynomials. But not every sequence of moments polynomial will give you orthogonal polynomials. But we will study this later. Okay, so now I'm going to give you another definition or different definition of orthogonal polynomials without using measure or weight function, okay? Using only the linear function. Okay. So definition, another definition. Suppose that let L be a linear functional defined on the space of polynomials. C or RC, or maybe you can think of this, or C of X or something like that. Yeah. And by the way, a linear functional, if you haven't heard of this, this is just a function. Linear functional is a function. It's another way of saying a function. If a function, what is a function? Function is like f from R to R, then it's usually called a function. But linear functional is a function, something like it sends a function to a function. So this is a function, but it's more common to call this a linear functional. So a functional basically means a function that sends function to some number. So Anyway, it's just a terminology. So linear function is just a function defined on the space of polynomials. And let's say a sequence. Let me write this way, a sequence. This is an OPS with respect to this linear functional L if the following condition holds. So first, the same condition, n, for all n of course. And second, L of p n x squared is non-zero for all n. And 3, is 0 for all m n different. Right, so now you see we have additional condition here, which was not there in this case. But like I said, this is not necessary here because it is automatic from this condition. Yeah. I'm not going to go all the details about this measure theory or integral stuff, but if you think about it, yeah, you can convince yourself that this is not necessary because here, let's remark, note, maybe I can note, if you integrate a positive function like f of x, w is going to be always positive if fx is a polynomial non-negative, always non-negative. It's automatic. And that's why we don't need that condition. Okay, yeah. So a nice thing about this is that we don't have to worry about the measure or weight function. So we will focus more on this because our goal, after all, is to study orthogonal polynomials combinatorially. So we don't want to spend too much time on measure theory or measure weight function, things like that. So we will use this as our definition of orthogonal polynomials. Okay. By the way, because we talked about the Chebyshev polynomial, let me give you a brief remark about the Chebyshev polynomial. Because so far, there's no hint about why combinatorics can appear in the orthogonal polynomials. It's not clear at all, right? But if you look at the Chebyshev polynomials, the moment of the Chebyshev polynomial can be computed like this, mu n. So it's -1 to 1 is x to the n, the Chebyshev weight function, 1 minus x squared dx, right? So if you just do the computation, then you will see that it will be 0 if n is odd, and if n is even, and it has some interesting number like pi over 2 to the 2n choose n. Okay, it's just small, but if you look at this, let's forget about this vector. But 2n choose n is a binomial coefficient. 2n choose n is the binomial coefficient, which is like which appears all the time in combinatorics. So if you are combinatorially minded, then you will see, you might be wondering, is there some kind of combinatorial reason behind this integral? And there is, and we will see this, later. Once we develop some combinatorial theory of orthogonal polynomials, then we can prove this without doing any integral, but you can just prove this using combinatorics only by counting some lattice path. That will give you a proof of this, which is quite interesting. And not only this, there are many examples of orthogonal polynomials whose moment sequences have very nice combinatorial formulas. And we can prove them using using combinatorics only. Okay, so let me give you another example. It's called a Charlier polynomial. So, the Charlier polynomials let me denote this by P sub n, just P sub n. These are defined by, we just have explicit formula, so Pnx equals summation k from 0 to n, x choose k minus a to the n minus k over n minus k factorial. Okay. Here, this is the binomial coefficient, so you know what these are. So maybe in your high school you use a different notation, something like this, but it's more common in math papers that we write binomial coefficient like this. So this is n factorial, k factorial, n minus k factorial, right? So it's called the binomial coefficient. And also it has nice combinatorial meaning, like a number of ways to select k elements from 1 up to n, right? So it's a nice number, just a non-negative integer. But this x is a variable, right? So what is x choose k? That can also be defined here. X choose k means x times x minus 1 times dot 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 x minus k plus 1 over k factorial. This is consistent with this definition because if you, n factorial is n minus 1 dot 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 1, and this is n minus k dot 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 1. So if you divide this, then you get exactly this thing with n over here. So they are the same. When x equals integer, of course. So this is a polynomial in x, right? Of degree, it's a polynomial in x of degree k. So it is a polynomial, so you add polynomial, so the result will be a polynomial. So that's the definition of the Charlier polynomials. And these are also very famous, one of the famous orthogonal polynomials. So we will find some orthogonality, but it will be a little different from the orthogonality that we saw from Chebyshev polynomials. The reason why this is called binomial coefficient, I guess you all know this. 1 plus x to the n is equal to k from 0 to, okay, let me write this in a general form. You probably remember this from your calculus class. So it's infinity. Alpha choose k, x to the k. So now it's an infinite series. If alpha is a positive integer, it's going to be a polynomial. But if alpha is not a positive integer, it can still be defined, and it's a power series. And this is a binomial, and that's why it's called the binomial coefficient. And now let's see if we can find some orthogonality for Charlier polynomial. So to do this, we need to consider the generating function for P. So let me copy this just that you can see. So the generating function Pnx is, when we have a sequence of any quantities like a0, a1, a2, dot, 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 the generating function for that sequence means, okay, let me recall you here. The generating function. This will be a very useful tool and important tool in this semester. Generating function for a sequence an. The sequence is this. It's a power series where the coefficient of x to the n is an. So generating function is nothing but a way to record a sequence, just a power series. But so it's really the same thing as just a sequence. But because it's a power series, we can do like multiplication, addition, division, things like that you do when you as you do when you do calculus. So that's just the terminology. So the generating function for this, of course, means summation, maybe okay, n from infinite. This means the same thing as this, Pnx. But we don't want to put it like this because x is already here, so we're gonna use another letter like this. So I'm gonna denote this by g x comma w. Okay, so this is the generating function for. This is the generating function for the Charlier polynomial. Okay. Now we will compute this a little bit. Let me over here. Now let me copy this formula over here so that k from 0 to n, x to the k, k wn, right? And now let's do some computation. If you do this computation, again, I'm gonna omit the computation. You can, using this formula, you will be able to do this. Summation n from 0 minus a to the m factorial w to the m. Why is this true? Let's see. It should be, just a change of variables, I think. This is n. This is, because of these indices, k becomes now n, n minus k becomes m, then you get this. Okay, it's just a change of indices. It's nothing but it's as simple as that. And then I separate this because now n equals k plus m is going to be m, like that. A simple computation, nothing serious. Okay. Now, what is this? If you look at this, have you seen this before? Yes, just a previous slide. It's a binomial series, so it's going to be a 1 plus w to the x, right? 1 plus w to the x. And if you look at this, then you will realize, it's going to be the exponential function. So it's exponential function minus a. Okay? So it has a simple formula. The generating function has this simple formula. Oh, no, sorry, aw. We combine these two together, so it's like aw over here, so minus aw. And from this, we do a to the x. You may wonder why I'm doing this, but the reason is if you do this, we can find something interesting, right? You will see why I'm doing this. W. This. Now we have this formula. This is very easy. If you compute this, it's going to be minus e to the a vw a 1 plus w, v1 plus w to the raised to the x, right? Because we have this formula, just substitute there, we get this, okay? Now let me erase this part. So we have, okay, now let me write the generating function formula like this. A to the k, g, kv, g, kw, k factorial. Then this is summation k. Now I'm gonna replace this by this, where now x is now k. So a to the, e to the minus a v plus w. Maybe I can find it over here. A 1 plus v 1 plus w raised to the kth power over k factorial. Okay. Here is k, this is k, so just put it there. Okay, so now this doesn't have any k, so you can pull this out, right? But now if you look at this is again the exponential function. So this can be written as e to the, just here, e to the minus a times v plus w for the common factor, and the other factor is e to the a 1 plus v 1 plus w, right? So we can simplify this. It'll be e to the a like that. Or just the same thing, but e to the a, so for e to the a vw. Okay. So, but let's compute this again then. E to the a times summation k from 0 a v w to the k over k factorial, right? This can be computed. So important thing here is that v and w can always come together. That's the thing that we wanted to find here. But now, so I computed this using this kind of computation, but we can also compute this using just the definition of this generating function. Okay, I will do this again. Okay, well, let me summarize this in the next page, and then I will do the same computation again with a different definition. This is what I need. This is what I don't need. But on the other hand, the left-hand side is also generating function for P, the Charlier polynomials, right? So this is generating function for K. Just look at this. Just where is it? So this and this are gonna be this. So summation. I'm gonna combine them together like this. P sub mk, P sub nk, Vm, Vn, right? Because this is this is this, okay? Oh, W. Is that right? Now, let me change the order of the summation. Mn greater than or equal to 0, and maybe I can combine. So k from 0 to infinity, Pmk. This is just change of summation, the order of the summation. And this doesn't have k in it, so like that. So we also know that this must be equal to this. But let's compare these two. I briefly mentioned earlier that V and W always come together. That means if M and N are different, then this must be 0. And if they are equal, it's non-zero, and that is exactly this. So from this, we can conclude that summation K, Pmk, Pnk is 0 if these are different, and it's non-zero, and exactly we know what this is. These times, or maybe these together, I guess, e to the a to the k over k factorial if m equals n. Okay? Oh, this should be n, right? Because n, if these two are equal, then we are looking at this term, so it will be this. So, in other words, we can say, but if you look at this can be understood as a linear orthogonality. If you define your linear functional in a nice way, so if we define a linear functional L by this formula, f of x summation k f, you just evaluate the polynomial at k for every integer, non-negative integer k, and then you sum this. This is a linear functional, and it'll converge for every polynomial. And so it's a perfectly valid linear functional, and you can conclude that this Shallier polynomials is an OPS with respect to this linear functional, right? So Shallier polynomials is also an example of orthogonal polynomials. But the orthogonality is defined slightly different way. For Chebyshev, we defined it where the linear functional was given using integral over some weight function. But actually, it's still possible to express this using integral. So note, it's possible to express L using integrals. So, but it's like a Riemann-Stieltjes integral, which is like, okay, let me just write it. So it's like minus infinity fx d phi x. So Riemann-Stieltjes integral. Riemann-Stieltjes integral, where phi is a function, say, it's a weight function, or step function actually. The weight function is a step function. So step function is like, you, for some interval, you just, it's constant, and at some point it jumps like a something like this. The largest integer less than or equal to x. So with jumps of magnitude, say ak over k factorial for each k. So if you don't know what Riemann-Stieltjes integral is, then don't worry about it. You're not going to use this. I'm just telling you that it is possible to write this in using integral, like a Riemann-Stieltjes integral. So, but our focus is, of course, combinatorics, so we will not worry too much about measure theory or integrals, but people who do orthogonal polynomials, it's an important problem to find the measure of the linear function like this. But for us, we will just forget about them. We will just see, we will be happy without knowing all of this in our class, okay? Any questions so far? Okay, so now, if you are a combinatorially minded person, then if you see a formula like this, then you may wonder if you can prove this combinatorially. So, actually, it is possible to prove this directly using just this formula. But actually, this is essentially the same as these generating function techniques. But if you don't like this proof, then it is possible to prove this combinatorially. But in fact, I will explain I'll give you another proof of this in the next lecture. Okay, so if there are no questions, then I will stop here for today. And yeah, thank you very much.